Okay, so let's start. I think I think those of you who were falling asleep, hopefully we have you back. What I'll try to do is now we have about an hour, so we'll cover some of. I think Professor Kannan, Mahajani, and Shastri have already covered the basics. I'll try to do more of the nuts and bolts details. Also, I'll try to cover some of the mistakes I see often when students contact or we thought some of the common instructions that we give, we'll try to cover them. Also, the second part is like Professor Mahajani said, what comes after the process simulator, right? So there is stuff, there is the bare minimum requirements, but a good project report has a lot of other stuff. And what I'll try to do today is at least expose you to what those elements are. And then later in the semester, if we need to do more, detailed overviews of some of those areas, we are happy to do them. But at least we want to, give you a pep talk or motivate you that, don't stop at a process simulator. You could do a much better report. So we'll start there. And yeah, as you can see, this is a very important class. I don't think you have ever had so many of us professors in the same room for a class. So especially this year, because there's 2 batches together. Right, so what I'll try to do is not tell you how to do, like I'm not going to the design of it. Mostly the 4th year guys have already had a class, or you already had mass transfer, heat transfer, reaction engineering, where you've done most of it. What I'm trying to do is do a bit of a refresher and maybe point you to the references, right? The right sources, the right books, and some of these books you may have used, some of them you may not have. And I don't think these are the only ones, but at least if you're stuck, you should, and I'll post these slides. So whenever you are stuck, you should be able to think, where else have I missed? Should I look in a book for certain aspects in it? Other than that, it's more a tips and tricks of the trade sort of thing. Like when I want to find out pricing or market capacity, where do I look at, right? So I'll try to share some of that with you and, hopefully, so that's the structure of the talk. So let's start with resources. So my talk will be in the, I'm trying to cover actual stuff. Some of this you might have already seen. And some of it you might not have. So just settle down a bit. Right? So Perry's handbook, an age-old resource. But even today, if you are stuck, and I see a lot of guys say, okay, how do I design a crystallizer? We have never been taught in the class. If you have a situation like that, the first point to start should usually be Perry's handbook or one of the other handbooks I'm showing you. Because this is a distillation of intelligence. And sometimes what I see is people are tempted to look at articles, right? But there is a place for scientific articles and there is a place for textbooks and handbooks. And let me try to explain what that is. Suppose you want to know whether a reaction works, what temperature, what yields are you going to get. That's the place to look at an article or a patent, right? That's going to give you that input. But if you try to look at how do I design a pump or how do I select a centrifugal pump, usually you will be better off looking at a textbook or a handbook because that's not, you're not trying to find an innovative pump, right? There'll be articles, people try to find different things. But whatever is tried, tested and condensed makes it to an handbook, right? So if you want to find out the design methods, etc., look at a handbook. If you want to know specific kinetics, VLE data, whatever that is, usually an article is, so don't make the mistake of not. Usually what I see is it's very easy to search on SciFinder or Google Scholar. So when people are stuck and they want to design a crystallizer, they look up on SciFinder and then you get some articles, but they may either only cover a part of the topic or it may be an innovative process or something like that, right? So Perry's handbook, even for a lot of, I won't be able to cover what all is in it, but for materials of construction, great chapters which tell you what materials you can use. For just thermodynamic data, for design processes, for equipment selection, right? When should I use a centrifugal pump and where do I want to use a positive displacement pump, right? Perry's handbook is a starting point. For thermodynamic data, I don't know how many of you have used NIST. Luckily, when you have DWSIM or ASPEN, a lot of data is in there. But suppose you want something very specific and it's not there, don't forget to look up the NIST and it's all online, which makes it very easy. I'm just showing you a typical material selection table, just in case you have not seen it in any of the other courses. So, if you're trying to select what material of construction to use, and you'll have a lot of different reactants, storage tanks, whatever it is, how do you find out? Look at a handbook, and Perry's is not the only one, but a lot of handbooks will have tables like this. They'll also have similar ones for piping systems. And let me illustrate something, right? Sometimes you have something corrosive, so mild steel will not work. You go to stainless, maybe stainless doesn't work. Now you come to Hastelloy, right? Your reactor is high temperature, you're using Hastelloy, fine. Now the difference between a good enough project and a really good project is One guy will use Hastelloy for the reactor and all the piping in Hastelloy. Will work. But another guy says that, okay, the Hastelloy for the reactor, of course, I'm using high temperatures, high pressures, metal is imperative, so I use Hastelloy. But for some HCl feed piping, do I really need to use Hastelloy? He looks up a piping compatibility and says, okay, piping is only at low temperatures, I'm going to use a polymer, right? I'm just giving you an example. So a project is about creativity. You don't have to find the one right answer. There is infinite ways of designing the same plant at the same capacity, but when you look at it, you sort of get an idea how much thought has the group put into it, right? The easy thing is you could choose titanium, you could choose tantalum, a lot of super expensive materials. At the end of it, like Professor Mahajani says, the plant has to make sense. So a lot of very expensive materials get used for plants that are producing really cheap products. Sodium chloride, there's a lot of titanium exchanges in there, right? So at the end, the capex has to balance out. So that's what I'm telling you, that put some thought and creativity. Is the material you're using, it may be compatible, but is it commercially the right material, right? And so a lot of that data is out there. Choosing things like vacuum pumps, a lot of fine chemical distillations, or even in other commodity chemicals, you'll see a lot of vacuum processes. And from last year, like Kannan said, we had industry experienced people, and typically the critique is of a following nature. Suppose you need very high, you need a 1 millimeter vacuum, and you just use a vacuum pump, or you use a single stage ejector. It may not be possible to get there. Now the question is, how are you supposed to know as students doing it for the first time? So I think the process design course is a great spot to read a lot of material, right? So look up, this is from Perry's handbook. There are tables out there, there are selection charts out there, you just have to look them up, right? You have to look them up. So I'm just exposing you to the sort of stuff which is out there. So the table here, for example, if you choose the vacuum level, it will tell you what the options are. What are the feasible options, right? This is not a mathematical thing. These are more like heuristics, thumb rules, and a good design project is going to use a lot of them. So suppose you have a certain pressure and you say, okay, I'm using a 3-stage steam ejector. And suppose the examiner asks you, why did you use it? And you say, okay, I looked up. Now that demonstrates a certain higher degree of thought than just picking up a single vacuum pump, which may not even work for that level of vacuum. Next. Two other handbooks, Ullman's and Kerr-Kothmar. I don't know how many of you have used them, but a great starting point. If you are lucky enough to have your chemical in one of these, it will already give you a lot of references, right? One thing is to use Google Scholar, find whatever is new, but the other one is to go to an article. If there is an article on acrylonitrile, and most of the common commodities have articles here, and they'll give you a lot of, they won't give you a design, but they'll give you a lot of places. Here's a study on the properties, here's a study on toxicity, here's the typical way it's done. So don't forget these handbooks. Now coming to search tools, I hope you've used SciFinder. If not, I think we have a subscription. So that's a great way to find kinetics, articles, whatever data, etc. is required. But this is mainly going to target scientific articles. So if there was a journal article published, you would get it in SciFinder. Of course, it also looks at patents and some other sources. Two other tools, Google Scholar for papers and Google Patents for patents again, right? And normally I use multiple tools because sometimes for whatever reason, one tool will not discover a resource, and in your group, you have 6 people, so really there's no excuse not to exhaust all these tools, right? You have 6 people a whole semester, and in spite of that, in the references, typically I find people miss a reference. Like if you say, okay, there is no kinetics on this, it's quite rare. It just means you have not done a search which is exhaustive enough. And give it enough time. If you try to do 15 minutes of a search, you will find the same articles. You will have to give 2-3 hours, sit at it, and then you will start discovering patterns and other things that you want to find out. Reaxis. The chemists typically use this tool a lot. Chemical engineers, I don't know if you've used it for a course or something like that. Lot of great filters. We have a subscription, I believe, at IIT. And so you can do things like find reactions above a certain temperature, or where the yields are above something, or only find preparations and not, all kinds of things. It's a very powerful tool in order to discover who has done what. And you don't always need to find the article. Sometimes Reaxis will have a summary, so that just looking at the summary on Reaxis, you'll figure out if it's worth digging deeper or it's not something which is very interesting, right? So that's Reaxis. And again, I'll share the slides. All I'm trying to do is make sure you cover these tools. If you're stuck, make sure you've seen the tool, and that way the quality of the data you find will hopefully be better. Patents. A lot of patents are US patents. So if you are looking at US patents, the US patents website has a great search and whatever, and they have a lot of advanced filters, right? So sometimes if you just look at acrylonitrile, you'll get a lot of guys using acrylonitrile. But if you use it in the title or you combine it with the right keywords, you're probably more likely to find the right patents. And remember, for this course, I don't think we are looking at infringement. So patents for you are not a way to know whether you're infringing something. They are a way for you to know. What's the most important section for you in a patent, you think? Anyone? The examples. Because a lot of the examples section may not give you direct kinetics, but suppose you are in the fine chemical or specialty chemicals, you will have an example where they say, okay, I mixed these things, I heated them for 3 hours, and now something was formed at 98% yield. So that 3 hours is the crucial parameter. So learn to read these patents, focus. The claims don't matter much for this course, because I don't think you're doing an infringement or a freedom to operate study. What matters for you is the example section, because there'll be a ton of useful data. A lot of people say, I don't know what byproducts were formed. In a patent, normally there'll be an example, and that example will have a GC or a GCMS, where there'll be a table which says these were the other things which were formed, right? Because the patent is supposed to disclose all of that. Similarly, if you want European patents, the European Patents Office has a website called eSpaceNet. All of these are free websites. And so if you want patent coverage, this is another good resource to look at to make sure you have not missed something. If you have any questions, yeah, interrupt me or raise your hands, right? If something is not obvious, let me know. Fine, and mostly I feel that people have just very rarely do I come with a group where the questions they ask, and if I ask them, have you looked at patents? Well, they're probably not discovered. And that's why I'm giving this talk, to make sure that, before you conclude that I'm not finding something, go through these resources. There's still a chance that you don't have anything, but at least you will say that, okay, I've looked at all of this and I'm not finding it, right? Give it enough time and you'll find something. Coming to the report, I'm just going back and forth. Personally, I think you should focus more or most, you always need to prioritize on the flow sheets, the tables and the figures. A lot of people, when they read at a report, these are the first things they're going to do. Right? So suppose I see your PNID is excellent, or your PFD, like Professor Kannan said, has all the details in it. I'm not likely to read a long, boring wall of text. Right? Most people don't want to double check all your calculations. If something doesn't make sense, of course, I want your calculations to make sure that you're not bluffing or you've not made a mistake or something like that. But I would say, and this is a flaw I find a lot of people, because it's easier to type text, right? Suppose I do a design. A lot of the design chapter in the past I've seen will have a lot of paragraphs and paragraphs. Even the symbols are not there. Whereas what you really want to see is the figure. If you have one figure, one good PNID, you don't really want to read all the text, right? So if you want to prioritize, put a lot of attention into every figure in every flow sheet that you have. The PFD, the PNID, if those are great, that's what conveys. Like, even if, say, as examiners, as professors, we are going to look at it every week. But suppose at the end of the study, you have one guy who has 1 hour or 20 minutes to quiz you on it. Which diagram do you think he goes to? The flow sheets. The flow sheets are the most important part. What I find is a lot of you are not used to using tools to sketch, but you know the tools to type text. Hence, reports become heavy on text, but do not use as many figures. All the figures I find are copy-pasted. You go to a patent, copy-pasting a figure is easy. To the extent that a lot of time reaction chemistry, people will copy-paste from a patent. Learn ChemDraw, learn how to do a balanced reaction. It takes some time to master these tools. I would almost say within the group, I'll look at some software tools. Each one of you should at least master one tool if you're going to split the work. And that's how you get a good report. So I think Professor Mahajani covered this, start from conceptual design, and then we'll look at some of the other things that we are encouraging you to do this year. So this is what he mentioned, what goes after the process simulation. So I would strongly encourage, if you want a great report, you may not do it for all your equipment, but at least for some equipment or some lines, there's 5 things. So these are not captured by Professor Kannan's table. So these are sort of optional in that sense, but at least for the third year guys, we want to push you to do these. One is PNID, and I'll try to show you examples of each one of these so that you sort of know where we are going. So in a PFD, you will have all streams. You will know what the temperatures, pressures, flow rates are. But normally a PFD will not do things like, do I need a pump or a compressor? How do I control this particular temperature? Do I have a loop that controls temperature based on composition, based on level, something else? That's not shown on a PFD. But that's very essential to having a good process design project. So that's the PNID. And you've done the PNID, right, in some course? Maybe process control. So you've seen PNIDs, hopefully. If not, a lot of great resources that I'm showing you today will have details about what a PNID is. Process safety, like sustainability safety is another important aspect. We would love to have you do an HAZOP of at least one equipment or a few critical lines. I'll show you what a HAZOP is and what's contained in it. And then, I'll point you to resources, or later in the semester, we could have a lecture that goes into more detail of a HAZOP. Plant layouts. So what's a layout? How is the equipment placed, right? At a glance, if I want to see what are the sections in your plant, do you have a distillation section, a tank farm, how many tanks are in a tank farm? And in fact, this is a very important thing if you really want to be an entrepreneur, because you want to know, do I need 1 acre, 6 acres, 2,000 acres? How big of a plant is there? And these are things which take a lot of judgment. Fortunately, there are ways to, if you read a book or if you read some of the things, you'll probably get a hang at it. I'm not saying these are easy things, but you are 6 guys, 1 semester. I think you should push yourself to do more. 4 is mechanical drawing, where you're already doing it. I think the flaw I see, or the gap I see, is you're focusing on just the calculations, but I rarely see any equipment drawn, right? So if you design a distillation column, normally the way engineers talk is you would have a sketch where you show the dimension, how many nozzles are there, what's the thickness, a detailed sketch, right? And we'll show you the tools, and this year we're doing something new there. And finally, equipment data sheets, we'll talk about what those are, right? So that's a P&ID. This is a P&ID. I'll zoom in, and like Professor Kannan was saying, on this, you may not be able to see something, but on the next one, as you zoom in, so a lot of engineering drawings are normally printed on large size. Of course, you may not print it, but at least figure out how to work with Word or something like that, so that you can draw something, so that I can zoom in and everything is legible, but I can still zoom out. So there is an advantage to this, right? Sometimes you want to see everything on one page, sometimes you want to zoom in, and this is just mastering your tools, figuring out how to do it in the right tool. But now this is a P&ID of a distillation column, and you'll see stuff like level gauges. Your P&ID may not have all these details, but at least think through, what are you measuring in a distillation column, right? So first time I did a P&ID when I was a student, you are tempted to control everything, and then you have a degrees of freedom issue, right? If you have the level in a column, you can't control both the inputs and outputs, otherwise the loops are fighting each other. But you will never discover this unless you try to make a P&ID. Right? What are the things that you should really control? And a lot of the concepts from the process control course, cascade control, split range control, you will find them in action when you start thinking about, how do I control the temperature of my reactor? Should I control the cooling fluid? Should I change inerts? Should I change the temperature that the input is coming at? A lot of parameters are there. And that's the exciting part about process design, because you don't really have constraints. You're debating amongst yourself, you're telling the professors why you did a certain thing, and we are trying to gauge whether you have thought that through, right? So P&IDs, I think we would strongly encourage, at least for one equipment, you should do a P&ID. So that should include your control loops, what are the gauges, are you measuring pressures, temperatures, is there a pump, and there is motifs. So for example, on this one, I show a typical control valve. Right? So a control valve will normally have a bypass. And if you have seen a lot of P&IDs, the reason for this is, what if the automatic controller fails, you don't want to shut down a plant because of that. So suppose the valve which says FO, suppose that valve has some malfunction, right? Because it's an automatic valve. You would want to have a bypass line that you're controlling manually in order to make it work. And then suppose you want to repair the valve, you want to shut it, right? So these are features of operability. And a lot of this you'll figure out by looking at P&IDs in handbooks and things like that. How do you operate a plant? I'm not saying you'll implement all of that in this, but think about these things, right? Suppose you want a control valve to be removed, unless you had those 2 valves on each side of it, how do you remove a valve from an operational plant, right? These are continuous plants for some of you that will run for 3 years at a stretch. So you definitely don't want to shut down the whole plant just because one valve went bad, right? And that's captured in a P&ID. Another motif, centrifugal pumps will often have a strainer on the input side, because if there is rust, if there's something, you don't want to come that into the pump and damage the impeller. So many of the pumps, what you see on and the symbols, I'll show you a PDF that you can look at later. Like engineers communicate with a common language, and for chemical engineers, this is standard symbols that go into a P&ID. So you don't need to remember them all, but start using standard symbols, because if you have something else for a pump, and this I've seen in a lot of reports, you have a distillation column, but they say distill and a circle, and somebody who sees it will assume it's a pump or something else, or a storage sphere, and then they find out, oh, that's a pump, right? So avoid that by sticking to standard symbols that, like here, the M is a motor, right? Anybody who sees it knows the M is a motor, whatever. So stick to standard symbols when you're doing these things. Operability again, so drains, vents. When you do a P&ID, suppose it's a batch process and you're filling a heat exchanger with water. Now, where's the air going to go? So now you need a vent. So these are features for operability which should be there in a good plant design. So we'll skip that. One point is, I don't know if you have seen this book, maybe you have used it. Have you used it? Conceptual design or? Yes? How many of you have seen this? No? Maybe some of you. Okay. So do a good conceptual design. This is a good reference because if you make a mistake, right, like if your concept is not sound, suppose you should be using distillation, but you're using liquid-liquid extraction for whatever reason, or there is an azeotrope, but it's a phase separation would have worked, but it's an azeotrope and now you are wasting a lot of time breaking it. So if you make a mistake at conceptual design, your Aspen or DWSM is not going to save you. So like Professor Kannan was saying, the very first week should be Excel, should be block diagrams, and don't hesitate to make a diagram, whether it's on PowerPoint. Like I've seen a lot of descriptions where people say, okay, I'll have a stream go into this equipment and come out. And then you have to read the description and anyways make a diagram mentally to figure out what's happening. And I sense a hesitation because diagram somehow PowerPoint or whatever, you've not done the right tools for making diagrams. So you want to just type everything out, but doesn't work. Even when you're comparing various routes, it makes sense for you to draw the diagrams that describe the various routes, okay? Yeah, start with an Excel. I think a lot of Excel features, I don't know whether, not just for linear, but you can always have a convergence loop that auto-converges on Excel. So Excel has become quite powerful, and I would do it multiple ways, right? So a simulator is much more powerful than Excel. But if you're getting grossly different answers, you at least have a check. You have a sanity check, you have a back of the envelope check that your simulator, you might have made a mistake somewhere. Maybe one of your loops has not converged, or whether what you thought was an equilibrium reactor is really something else. Things happen like that. So always do two different ways, and one of them can be Excel or even pen and paper, and make sure that what your simulator is producing is at least in the right order of magnitude. You know GIGO, the acronym, garbage in, garbage out, and that applies to a simulator. You might have an excellent Aspen simulator. If you're using the wrong model, your answer will be off. Any questions so far? I'm going fast, but you don't really need to pay attention to everything because you're going to have the slides. So, have you seen this book? Chemical Engineering Design. So this is by Coulson and Rich. And maybe a lot of these are really old books, but I think they're still pretty good for a process design sort of thing. So again, if you're stuck and you think that I don't know the procedure to design a particular equipment, it's not been covered in class, look at these books. And they will definitely have any equipment that you're talking about, unless it's super exotic, will be covered in all of these books. For example, one area that I've seen a lot of previous reports, this is from one of the previous reports. I don't see a detailed equipment list. And when I see a detailed equipment list, if you're saying, I've seen reports which say, oh, we used 8 centrifugal pumps. That doesn't mean anything. You want to have the relevant parameter for an equipment. So suppose you have a heat exchanger and you tell me I have a shell and tube heat exchanger and the volume is 3 meter cube. Useless, right? For a shell and tube heat exchanger, what's the parameter you want to know? Area, right? The rating parameter. So like that, for some, like if you have a pump, you want to know the pressure ratio, discharge pressures, flow rates. Have a good list of every equipment, because whoever the examiners who look at it for the price and things like that, they are going to look at the major equipment list. And many people will develop a feel for what's the really critical. Suppose you have a compressor with huge flow rate and a delta, a pressure ratio of 50. Now they're going to worry whether this is possible, right? So a good equipment list, it's a table with parameters. So now how is the book I showed you relevant? It's because if you look at the appendix, you will see things like equipment, specification, data sheets. Now you don't need to, and if you see this 10 points, it sort of covers most of the common equipment you have. Heat exchangers, vessels would be columns, distillation columns, absorbers, you have reactors, other things, pumps. And what the sheet will give you is a lot of the relevant parameters. Now, of course, you may not be able to find all of them, that's okay. But at least look at a sheet so that you know that if you're going to go to a vendor and say, I want to buy a shell and tube heat exchanger, he's going to ask you certain questions. And those should be answered by your design project, right? You don't have to build the whole heat exchanger usually, except for one chapter where you're doing a detailed design. But what if you are actually building a plant and suppose you have a compressor and you go to a compressor making company, they're going to ask you certain questions. And those are very well captured, say in Coulson, or other handbooks will give you data sheets as well. What I want to do is just expose that this is not like you don't have to sleep at night and dream up, right? You'll ask me, how do I know what is required for a particular piece of equipment? It's easy. It's all there. Just look at the right places. So this will probably give you a better design project because you're answering the right questions. Suppose you have a centrifugal pump. You've also already mentioned the efficiencies, whatever are the crucial parameters, so that then you can go and identify the right pump. So these are equipment specification data sheets. You may not do it for all small things, but at least for the major pieces of equipment, you should try to address. Take a reactor. One way this works is, this is like a checklist that you can tick off. Normally people will just mention reactor stainless steel, but any good person who's reviewing will want to know how are you cooling and heating. Is there a jacket? Is there a limpet? What is the design pressure on the reactor itself? What is the design pressure on the jacket? What is the material on construction of each one of them? And when you look at a sheet, you'll also read some things that make you wonder, what is this? But then you can always look it up, and that's how you're going to learn from the design course. Yeah, this is a snippet, and it's actually from one of the top ones, but look at his CSTR, right? A circle, which is not a non-standard symbol. And so what I encourage you to do is, even for the PFD or the schematic, use the standard symbols so that people at a glance know which is a column. Now, there is a distillation. Even if you had to do a block diagram of a distillation, you would show it as a tall, something which parallels the equipment. You don't always have to use the exact symbol, but that's what I encourage you to do. That makes it easy to understand. Like if you show a distillation column or a reactor using the standard symbols, it's going to be much easier for somebody who even sees your comparative flow sheets. Suppose you have A, B, C, 3 processes and you're doing a route selection. If you use, and I know it's more work, you'll have to figure out how to use your tools, and maybe you can't do it for everything. I mean, figure out how much time you have. But wherever you are going to do this, I think your project is going to look better. And if you want to know standard symbols, there are various ways. Even Coulson, Perry's has it. But there are places which tell you the standard symbols. And many of these will have 20 different types of pumps. You don't care. At least have pumps and not reactors. When you show a pump, show it as a pump and not as a reactor. That's all I'm asking. Right? It becomes easier to communicate as engineers. Yeah, standard symbols for columns, etc. So this is, I think, from Coulson, Richardson, they'll all have them. So it doesn't matter where you look, that's not important, but don't show it as something very different. Like don't show a reactor as a circular vessel, right? That becomes difficult. Now I go to nomograms. This is again from Coulson, Richardson. So one thing is figuring out what is the heat transfer coefficient. Now there are multiple ways. What I want to highlight is sometimes there are multiple ways to check things. One way is to, in DWSIM or Aspen, put in a heat exchanger and you will calculate the output streams and you will calculate what is your heat transfer coefficient. But I would always recommend also look up a nomogram or a table, right? And so these are very approximate, but for your initial design, this may be faster. And second, this provides a sanity check on your simulator. So suppose you made a mistake in the simulator and you have an exchanger which is water versus water, and suddenly you get a U value of 50,000. Now you should stop and think. You should recheck your calculations because based on standard sources, it's supposed to be between 800 and 1500. As you get experience, you develop a feel for it. But for starters, have multiple ways to check. Don't believe in the simulator blindly because the simulators are good. But if your parameters are wrong or if it has not converged, you are going to get nonsensical results. And that's how you end up with like a distillation column which is 1 kilometer tall, or like a heat exchanger where the overall dimensions are in centimeters, right? For a commodity plant has happened. But how do you avoid it? By doing multiple levels. And so I'm trying to point you that there are ways to do that. Now, pricing. Any questions so far? I think we went super fast, but yeah, I don't think we have enough time in this course. So, nothing? Anyways, so we come to pricing. One common mistake, Sigma, Merck, all of that will have prices. Like take acrylonitrile, right? What is the price shown here per kilo? Take a guess based on this slide. Per kilo. And this is where you learn the art of like, do you see kilo? You see a 1 liter price. What is the typical density? What do you think is the density of organics? 0.8, 1, 1.2, nothing outside that range. So let's assume a liter is a kilo for order of magnitude. And that's very important in a design project. You have to make approximations, you have to learn to deal with fuzzy data. So suppose you're doing a project on acrylonitrile and you looked up this data. What do you think the price of acrylonitrile is? 8,000 rupees a kilo, right? What do you think the real commodity? Suppose Professor Kannan told you design a plant for 1 million tons of, like we are doing the largest plants in the world, right? 1 million tons or 500,000 tons. What do you think the price is? It's around less than $2. So at least this tells you the envelope. If you are getting it from a laboratory chemical, that's probably the most expensive. Your real stuff has to be way lower. Now the question is, how do you get real prices? Now there are various ways. There are websites. Now the rules have changed. Now we no longer disclose as India because there's a competitive disadvantage. But till like 2018-ish, a lot of the export-import shipments, the pricing used to be disclosed. Right? So there is a site called Zauba, and so that they have, right now they can't disclose a lot, but in the historical data, you can easily see and look at the quantities. So through Kandla from Turkey, 400 tons. So acrylonitrile is a commodity product. But this gives you several things, like this is market intelligence. It also tells you how things are coming in. Is it coming in glass bottles? No. So it's coming in really large quantities, either a chemical tanker or a container or several containers. Price per unit, $1.37. So maybe 120 rupees, 130 rupees a kilo. Definitely not 8,000 rupees. So learn to find the right sources for your raw material, not just product pricing, even for raw materials. I've seen people use the prices from Sigma, and then you'll have caustic soda and the price will be 500 rupees a kilo. All your estimates will be off. So learn multiple sources and try to figure out what is, and typically for the larger quantities, the price will be lower. So for small quantities, price is high. For example, the second row is only 45 tons. Price is a little higher. How it varies will change, but try to look at these sources. Another source is Chemical Weekly. So there's a magazine called Chemical Weekly. It comes every week. And at the back of it, or every couple of, and I think we have a subscription here. So you have some prices. Of course, these may be somewhere between a Sigma, but they're closer to the commodity price. The commodity price may be a little lower, but these prices are much closer to that. So that's another way to check. The best way for commodities is to use sites like Platts. Platts is a site that is for commodity traders. So for all the common stuff, caustic, styrene, benzene, toluene, you will have a daily price from Platts. Unfortunately, the databases are not open to everyone. However, you don't have to worry. So Platts, and there is something similar called ISIS, they keep publishing articles. So this is an article from November 4, and of course you are not an energy trader, so you don't need to do it every day. But you will see a lot of articles where they are talking about, if you look at it now, the price in China is mentioned, right? So look at these very reliable sources, because in order to sell their products, they are having articles which come out. And of course, we'll also try to see if we can get you some subscriptions, but a lot of these things are expensive. But this is another way of getting prices. Look at articles. Look for capacities as well as prices. One way is to look at publications like hydrocarbon processing or chemical and engineering news, because whenever somebody builds a large plant, or even Chemical Weekly, any large plant in India makes it to the Chemical Weekly news feed, always. So suppose you want to know who's building large plants, what capacity plants are there, go to some of these magazines, search their archives, and you will find, you'll find somebody built a plant of X capacity or Y capacity, or they'll talk about how there is a glut in the market and some guys have shut down, or how there is a shortage and prices have shot up. So articles of this nature are normally free and open because they want people to read them, right? And if you look at the articles, you'll find out. There's a bunch of market report websites. I don't trust any of them. Most of them don't even have a report, right? So some people are tempted, oh, there's a website saying, pay me something and get a report. Most of them will produce the report after you pay them, right? So these are all fraud. Mostly they're all fraud. When in doubt, you can ask one of your professors. But unless it's a reliable, large magazine, and there's no point in those market reports, because this is a project, so you are supposed to do a report, right? You are the guy producing it, so why pay the site? Doesn't make sense, don't cheat, and it's not going to help you. HAZOPs. So typically the point behind a HAZOP is you first should have a PN/ID ready, right? So choose an equipment or a couple of critical equipments, have the PN/IDs ready. What is the role behind a HAZOP? Oftentimes plants have blown up or accidents, explosions happen because a certain piece of equipment fails. So suppose you have a reactor. And yesterday in CL678, we saw a video where there was some blockage in the cooling line, and it was a highly exothermic reaction, and the reaction blows up. if a HAZOP had been done, right, what you do is, in the real industry, you would have a smart set of guys. You would have a mechanical engineer, an operator, a couple of chemical engineers, and sit together and go line by line. So you can't, of course, we are doing a simulated HAZOP, but it still makes a lot of sense for you to take your crucial equipment, say an exothermic reactor, and look at every line in your P&ID, and 6 of you sit together and say, what happens? So suppose it's cooling water. If flow increases, high flow, usually not a problem. But if there is no flow, or if there is less flow, now you could have a problem. Now the question is whether you would have a runaway reaction. This is the discussion you should be having. So that's the point behind a HAZOP. Systematically go through each line and figure out if the pressure increases, what happens? Is it credible, right? You can't put, and now what do? Suppose you have something very critical, you might put an interlock. So you might say that if the cooling water fails, I will have something where my feed is shut off. You might put an alarm. For critical, you don't put it for every line, but that's your judgment call. Is this a critical line where if something fails, you're going to have a catastrophe? In some cases, you may just have a standard operating procedure that we say, okay, it's too expensive to do it, but the operator every morning has to go and check whether it's working. But unless you document it, people are not going to do it. And that's the role behind a HAZOP. So make a P&ID and use a HAZOP. There are excellent books about it. I'll show you. This is an example of a HAZOP. So, so these are the guide words, sorry. And at the end of it, you'll come up with recommendations. Certain cases, you say, no, I don't think this is catastrophic, or I don't think it's very low probability, so it's not going to happen. Then you ignore it, but you document it. That's the role behind a HAZOP. If you want to know more, Trevor Kletz was sort of the very famous guy in the process safety area, and he has a whole book on HAZOP. So if you want to, at that point where you come there, you want to know more about it, there's always great resources. But if you do a HAZOP, you're going to go more on the process safety side, just like sustainability. And I think the people who read your report are going to be impressed that, okay, you have given it a thought. You may not do it for all the lines. It's going to take a lot of time. But suppose you did it for 5 lines, 6 lines, the critical ones on a piece of equipment, it's going to have a report of a better quality. Because just like sustainability, which Professor Shastri was talking about, you would have now covered safety. Okay? Questions? Should I slow down? So now plant layout. This is again, we haven't done a lot of it in previous projects, but we are just discussing amongst ourselves that, okay, if you want to have a great report, if you've gone to course on wheels, or if you've seen any plants, right? If you've seen accident reports, there's always a layout. So what does the plant layout look like, for example? And there's a great book again on it. A lot of these things you are not on your own, and I'm trying to show you the books. There are like 200-page books about how do you do a good plant layout. You just have to know what those are. This is the layout, right? And so that again, it needs some drawing, but the quality of your report looks better if you draw it out. Don't just say that, okay, I have 3 heat exchangers in the top left corner. That's not engineering. And this will indirectly allow you to use the tools. Forget layout. If I told you right now, draw this, how many of you, to somebody who is competent, it should maybe take an hour or 2 to draw this out. Suppose I told you, just replicate this on a drawing and so that I can remove something. Are you able to do it? If not, you have to figure out the right tools. And see, there's some way of doing it. Most equipment, you're showing the center lines and things like that. You're not showing all the details. What's the point behind a layout? To know how far you should keep things. Suppose you have a very high temperature reactor. Do you want a storage tank right next to it? No, right? A high temperature reactor, high pressure reactor is likely to have an incident. Suppose there is an incident and a small fire. If you have a very large 200,000 liter storage tank right next to it, then even a small incident will become a big one. And if you have visited plants, you have seen how the Reliance tank farm was far away from, right? That's why tank farms are far away. So that comes in the part of a layout. And of course, you're doing it for the first time. So we don't expect you will have the perfect layout, but at least come up with something so that you'll put some thought. Where does the fluid have to travel from, are fluids traveling? You also want to minimize the travel of fluid, or sometimes all the pumps are in a certain area. All heat exchangers might be next to each other. You have seen in plants there are normally compressor houses. So all the compressors, because they are large, they create a lot of noise. So if you have ever visited a plant, you'll see all the compressors right next to each other. Of course, that's very, it comes with time when you read. So there is a compressor house here to the top right. Why? Because you want to keep all the compressors together. But at least try to think, forget an optimal layout. Whatever is on your equipment list, you do your best and come up with some layout. And then we'll guide you, you show it to your professors, okay, this is the layout. At least it will give you some idea how big of a plant do you need. And you're not on your own, so I'll show you minimum spacing guidelines. So this is an extract from the same book. It has a lot of different equipment, right? So reactors, distillation, these are all heuristics developed over years of experience from people. So these are telling you how close can you keep, if you see a plant, you never see two equipment very close to each other. For example, if you have a flare, it generates a lot of heat and radiation. So you will have a long radius. You don't keep a flare right next to your tank farm. Otherwise, things will start catching fire. So this is what goes into a layout. We are not teaching you how to do a good layout, but we are at least exposing that if it's a good report, if you have to build your own plant, be an entrepreneur, you'll definitely have a layout. You never order equipment and then decide how to keep it. This will tell you whether you want to have gravity. Suppose you have 3 levels. Now you can consider gravity flow. A lot of fine chemicals of pharma plants, the tanks will be on the top level and the reactors will be at the middle level, and you will have a filter at the bottom level. At least make some layout. If you design your tanks at the bottom and filters at the top, when you show it to Professor Mahajani in the weekly meeting, he'll say, okay, why don't you do it some other way? But try to do it so that you'll have more insights about how you're going to build a good plant. So there is also a lot of maintenance and operability. For example, I show you a photo. What is this equipment, you think? Heat exchanger, and they're pulling out the tube bundle. Now I'll tell you how it goes on layout. So whenever you're doing a heat exchanger on the left, you see the area which is at the cross, that's the tube bundle removal area. So if you, for example, put a distillation column right next to the reboiler, you'll have no space left to pull out the bundles. This is the thought that goes. I'm not saying this is rocket science or this is like very difficult calculations, but I'm just telling you outside of the simulator, beyond that, when you see a good plant which is well laid out. Now, if you forget this, there are plants where when you want to pull the bundle, you'll have to take a shutdown and move the whole heat exchanger. Still happens, right? Because people forget a lot of this knowledge. So this is the importance of a layout. And so you'll have a lot of different ones. If you have an overhead heat exchanger or a vertical one, you'll still have to think what is the area in which you shouldn't put not just equipment, but piping. Suppose there's a distillation column, you can't take piping in that area, otherwise it will obstruct how you pull a heat exchanger. So I don't know how much of this you'll put in your reports, but I'm just trying to convey there's a lot of thought which goes behind. And if you don't put the thought as an engineer, the mechanic or the fitter is not going to do it. He will do it in the easiest possible way, and you will have a boss to answer when 6 months down the line there's a shutdown. No? People will ask you, why didn't you think of this? Right? And how do you think of all this? You read, right? You read, and in the handbooks all these things are mentioned. So you will have to do a lot of reading in this course. And a lot of good design is by looking at other things. So this is this Texas City accident. Remember the largest accident which happened at a refinery in Texas? In the report, you will have a layout, right? So a lot of this will come when you look at an environmental clearance or other plants. If you look at their layouts, now you start thinking, where do they keep a control room? You'll discover a pattern. All tank farms are very far away from the distillation columns. Things like that you will discover when you look at good designs. Also P&IDs. You should read a lot of P&IDs and you will get inspiration for what should be there on your own design. Common mistakes. Avoid handwritten pages. A lot of this is very basic, but I'm not making this up. This is there in actual reports which have been uploaded and I've seen in the past. Avoid it. How much time does it take to... You have 6 guys. So if I see a page like this, all this means is you did it on the last night before the final submission, right? It may happen once or twice in the intermediate reports, but all I'm saying is the final one, these days, processing is so easy, there's no real excuse for having scanned handwritten pages. In the chapter on mechanical design, so you do have a chapter and people are doing designs, my observation is everybody is trying to put a lot of text. You'll have text saying, this is my thickness. You'll have pages and pages of text. Who wants to read it? What I want to see is, do you have at least one drawing which shows the details? Suppose it's a heat exchanger, a reactor, whatever it is. And I think my judgment is because you're not very comfortable figuring out how to draw things, and maybe in real life you'll have a draftsman or somebody else do it for you. But I think it's a skill that you should still have, because if you have a great startup, you want to convey something, or maybe you don't want to convey, but if somebody, you want to buy some equipment and they send you a drawing, you should be comfortable interpreting the drawing, because you're paying a lot of money for it. And if it's your plant, you're the entrepreneur, you have to tell them, no, I want something made differently. And for that, you need to be able to say modify a drawing or edit drawing. So I would recommend that in your mechanical design, whatever you design, you should figure out how to do a drawing for it. And we'll tell you some tools later. Heat exchangers, right? You should, the tube sheet, how do you lay out a tube sheet? Otherwise, it's not really a mechanical design. You don't have to do it for everything, but whatever you choose for a detailed design, I think you should go into this level of detail, right? For whatever, suppose it's a heat exchanger, go into that level of detail. Another mistake, so this is from one of the better reports, but it says, I think the design is great, but it says process flow sheet in Aspen Plus showing a separation process. Now compare this to what, say, Professor Madhu shows you in the chemical processes. Do I know what the feedstock is? WTR1, ABSN. Right? So this is the output of DWSIM or Aspen, but that's not a flow sheet. In a flow sheet, you should have labels like Professor Kannan was talking about, label the key equipment, the key streams, show equipment with standard symbols, not the symbols on the flow sheet. You'll often have people ask, what is this symbol, the triangle? And that's just a join, right? In a flow sheet, if you have two streams, you want to combine them, you have a mixer or a join. In a real plant, there's no equipment. If it's two gases or two liquids, they're just going to mix, or maybe you have a static mixer, right? So this is a simulator output, but this is not the way you see a flow sheet. And how is a flow sheet? Look at Kirk-Othmer, look at any chemical processes, look at Professor Madhu's slides. That's a flow sheet, right? So that's what I want to emphasize. So compare this one with stuff like this, right? Much better. Now you see what equipment is there. So even in a flow sheet where you are trying to use equipment to sort of convey the form of the equipment, so that a reactor looks like a reactor, or a distillation column should look like a distillation column. And this is a proper flow sheet. So the bottom table will have flow rates. Don't forget to show whether, sometimes you have a two-phase stream. Then you need to show how much of the phase is vapor, how much of it is liquid, what pressures, temperatures, what are trace elements, right? So that happens in the table on the bottom, but see how well laid out it is. Because you can see the equipment, there'll be numbers for the streams, and those are in the table. So take some effort, but that's the difference between just a standard project and a good project. Bibliography, right? Don't just put links out there. If it's a patent, you want to know US patent, whatever, the name of the person et al., what are the patent number, you can still link, that's okay. But it's lazy to just put links in there because people then don't know, what's in this, people don't know, right? So find out any standard textbook or a journal article, and you will have a normal way of making a bibliography. These are all basic things, but I'm not making this up. These are from real reports that your seniors have submitted. And you have a whole semester, right? You have a lot of time to go through this and improve it. So unless you do it on the last day. Now this, the figure complete flow sheet for the process, it's just a screenshot from one of the reports, right? And yeah, I don't know what's S1. You have no idea. So don't just repeat the simulator output. The simulator is for simulations, but when you're conveying what you've produced to other people, you will have to use the right symbols and notation and things like that. One suggestion is hyperlink internally. A lot of people from many of the good reports already do it. So if you are having an introduction, I want to just click on 6 and go to the page, because a lot of design projects, you'll have to do a back and forth. And it's not very difficult to do it. Just figure out how to do it. That tells you whether you're taking that effort or not. This is a screenshot from a report. Now, if you see the x-axis, can you really figure out what is the unit, and could you have scientific notation, tons per year, right? To give it a thought. And this is one of the better reports. I'm not disclosing who the guy is. But again, on the y-axis, recovery. So what they're doing is, this is an absorber. As the amount of water increases, obviously the recovery increases. But think about what somebody would want to know. He would want to know the percent recovery, right? How do you decide? Now, suppose you keep putting more and more water, the recovery goes up. That's obvious. Now, how do you decide in a project where to stop? Should I use 49,000 or 5,40,000? Which one to use? How do you do it? It's an economic trade-off, right? More and more water is going to cost you more circulation cost or water cost. You'll have a utility cost. On the other hand, your recovery of acrylonitrile, suppose you have a 95% recovery, 5% is lost, right? So that is lost profits for you. So normally you're going to do a trade-off and decide based on that, how much of recovery do you want? So probably you want a percent recovery on the y-axis. And I see why people do this, because very often they do the easiest thing in the simulator. Whatever the simulator, this is on the sensitivity analysis chapter. So figure out what variables are the ones that your reader wants. Just don't do random variables. Another one is recovery of acrylonitrile or acetonitrile versus top stage pressure. There's no units on the pressure. So I presume this is bar, but I don't know. It could be tens of bars. So don't have graphs without axes. Again, I repeat, and use significant figures. Don't give me the pricing of a column to 6 decimal places. Very often, and it looks ugly because Excel produces it, but figure out how to set the number of decimals in Excel, right? Nobody's buying a column in paise. If you have a 10 lakh column, you don't really write 10 lakh 0.35 paise, right? People will laugh at it. So simple stuff, but remember it. Useful software, ChemDraw has a free trial, and there are of course alternatives. There are open source alternatives to ChemDraw, and maybe Priyam can tell you what they are. Even in SciFinder or Reaxys, there is a chemical drawing tool. You might use that. What you should not do is just pick up random snapshots from patents and articles. If you are doing acrylonitrile, if there are 4 reactions in it, you should type it out, because that's the way you balance a reaction. Sometimes people have unbalanced reactions, and the number of reports where the chemistry is never written out is incredible. I have a lot of reports I've seen where the chemistry is not really written out. They have described it or they have mentioned it in text, but you don't have a set of blocks with the chemistry in it. If you don't do that, your stoichiometry is going to be off. You will have a problem with your chemical kinetics. Everything's going to be a problem. So draw out a reaction. And it doesn't look nice to have copy pasted things with one font, 3 reactions, 3 more from another paper with a different font. You can very easily figure that this was hasty work. You have a whole semester, so you have no excuse not doing it. For making P&IDs, other kinds of diagrams, one option is Visio. And again, this is a matter of taste. People have a lot of software will allow you to do that. I recommend Visio because I think we have a license for the whole thing, and maybe the TAs will hold a session on some of this. But if you want to do a good P&ID, and what's a good P&ID? So lines shouldn't intersect, right? And that's quite difficult to do in things like PowerPoint. Like if you try to do a complex P&ID in PowerPoint, sooner or later your lines intersect. A good P&ID, lines will always break where they intersect so that you can trace them, right? And not even the circuit sort. You don't do those loops on a P&ID normally, you break lines. And things like Visio will do those auto routing and things like that. So make sure you use the tools, and it will help you later if you're doing other projects as well. And so now's a good time to learn. And I think so Visio is one option. Learn something else if you want. Whole point is, can you make a P&ID relatively rapidly so that it looks nice? Figure out whatever tool you're going to use. Lots of free and open tools we have. Now, when you come to mechanical drawings, there is things like solid edge. There is a lot of other options. But I would recommend, I'm probably trying to push you, but trust me, I've done this. And so this is not stuff I have done, but I have done models of reactors. And once you know a tool like solid edge, it's a matter of hours. It's not very difficult to do a model like this. But if you put that in your report, I think you're going to impress people. And so these days, it's all 3D model. Now, you may think, okay, this is mechanical engineering domain, but why not? Chemical engineers are supposed to know a bit of everything, right? So I'm not saying do it for all your equipment, but at least for your crucial equipment, the one you're doing a mechanical design for, try to find some program. Again, there are student editions for free available. Why not master them and have that equipment? Suppose it's a distillation column. Have a drawing of the trays. Whatever you're designing, once you have designed it, represent it. And I'm not saying do 3D, do a 2D drawing. 2D drawings are also great. Now, if you do a 3D, you can automatically ask the software to do a 2D, but do a 2D drawing. But do a proper mechanical drawing, because that's what your fabricator is going to want if you are actually going to build a plant from this. Another option, AutoCAD. The whole Autodesk suite, I believe, is free for students. And so I got that from their website, but somebody can check again. The 2 tools from that which are super important is AutoCAD for drafting, making things, P&IDs. Just like you could do it in Visio, you could also do it in AutoCAD. A lot of those capabilities are there. A lot of the templates are there. So don't really think you have to draw the heat exchangers from scratch. Both Visio and AutoCAD will have a template library where most of the heat exchanger symbols, etc. are already there. Right? So learn to be smart about how you're going to use these tools. The second one is AutoCAD Plant 3D. So this is a special software for chemical engineers, and it could help you make things like this, right? Again, it's a learning curve. I'm not saying it's easy, but I mean, you guys are all smart about learning tools. There's a ton of tutorials. You don't have to do it for your whole plant, but if you have one section, the crucial section, and you do a layout like this, I'll be impressed. Because it's not very difficult to do, but then I know you put the effort, and then you can actually visualize how your plant is going to look like. So I don't say that all the previous batches have done this, but we are trying to push you guys a little more. So this is, learn some tools. You have 6 guys. If each one of you masters a tool, you can very easily parallelize things, right? So in the first week, nobody's going to ask you to do that. But if you learn the software and try to replicate things, then by the end of the semester, when you're ready to do a design after the mechanical design, you're ready to use the tool. So you have the whole semester really to learn the software, right? One day a week, you're going to be sitting here. I think smart people among you, within 3 hours, you'll sort of master it and know how to use it. Now, let's come to design. So like distillation column, I present some examples. You will often have pack columns, right? Structured packings or random packings. One question people always have is, how do I find flood points? How do I know what is my HETP, right? Many of the vendors who produce these packings will have proprietary programs. Not all of them, but we'll figure out. We can talk to Silzer. So some of these programs will, if you put in, these are not design programs. So you'll put in the data from a DWSIM or an Aspen. And what this tool will tell you is, if I use a BX packing, a CY packing, how many stages can I fit in a meter? Or if I use various kinds of packings, how close am I to the flood point? So I've seen in the past, last year, people ask, what percent of flood point are you? And people don't have a good answer. And you can't do these packings with generic correlations. So one easy thing is use tools like this, Sulcol. Just put in parameters once your other design is done, and it tells you how many stages you're going to need. Another one is from Coq. I think KG Tower also, if you just put in your details, it's free to download and use. So these are tools that you would use in order to design, say, structured packings, random packings, right? Not the typical tray columns, but for things like that. But they even have tray design, right? Like what is your V point and things like that. You can always double check your manual calculations with a tool like this. Now we come to batch. Some of you have a batch plant and the question is, okay, it's not continuous. So what are some unique features in a batch plant design? So I just show you some. One is unsteady state, right? Many of batch plants will be unsteady state. The distillation will be a batch distillation. And so you have to use different tools, and there are a lot of tools available in order to model that. Sometimes even Aspen, etc. may have an unsteady state simulator in it. Distillations will be batch distillations. One concern is equipment utilization. So that's what I show on the bottom right. See, in a batch plant, you're going to have, say, 3-4 different equipment. You'll have a reactor. The batch may be 24 hours, but filtration may be rather fast. So filtration may take only 3 hours. What you're trying to figure out is so each row is a different equipment here, and wherever there's no color, this is idle time, right? The equipment is not doing something. So all the same color or the same batch. So it starts from V101, then goes to DF101. But once that is done, DF101 is free. So one thought, like in batch processes, a diagram like this. On the y-axis, which are the equipments you have, and on the x-axis, time. This is how so because I've gotten a question, what do I do for a batch process? Do I do a PFD? Sure, you do a PFD, PNID, but how do you convey a batch process? This is one way to do it. Equipment on the y-axis, and what are the operations on the x-axis, right? So this is how you convey how a batch multipurpose or even a single product batch plant, how are you going to use different equipment? Second, plot curves. So suppose you have a batch reactor. The temperature varies with time. Initially room temperature, you heat it up, you hold it at a certain temperature, now you cool it down. As you do it, suppose most reactions are semi-batch. So you'll take one liquid, suppose you take 300 liters, now the reactor is 300 liters occupied. Now you dose the other liquid another 500 liters over 3 hours. So the total volume in the reactor changes. These are things you want to convey for a batch process. How is temperature changing with time, pressure changing with time, total contents of the reactor, how are they changing with time? If you convey all that, so batch process is also very rich, but very often if you have not seen it before, you don't know what to represent on a batch process. So maybe this gives you some idea. If you're doing a distillation, you're to batch distillation, you're going to take various cuts. So you want to convey what is the composition of each one of the cuts that you're having in a batch distillation. Some more tips. If you're choosing collector, sometimes I get a tray column, but the diameter is only 500 millimeters. And then people will ask the examiners, oh, is a tray column available in such small diameters? How do you get better at this? Use the selection diagram. So what I show on the left side is a selection diagram. If you have the vapor velocity and column diameter, it will tell you what are the right kinds of collectors or what is the right type of column, whether a sieve tray is available or a valve tray, or do you have to switch. Normally for smallest diameters, you will have to switch to a pack column. So use these are there in a lot of places, but use these selection diagrams. On the right side, I have a HETP versus flow rate column traffic. Similarly, you have flood point diagrams. Many of these will not be in your regular textbooks because one way to design is, use an equation. But a lot of times, if you go to the vendors, whoever is selling you packing, Sulzer, etc., they will have a lot of data sheets. What I'm motivating you is switch between equation-oriented design and design based on data sheets. A lot of people love, and it's a realistic design, if once you have found out the numbers, you go to a data sheet, put in the right parameters, and actually convince yourself that the HETP is whatever or the delta P is whatever you have assumed, right? So equations are just one way to design. Often real design will be based on data sheets. Another one is selection for compressors. Based on the pressure ratios and the flow rates, how do you know whether you want to use an axial compressor or a centrifugal? So if you add this level of detail, like Professor Mahajani said, this is what comes after a simulator. But this is the real design. If you have a really small flow rate, you can't use an axial compressor. You have to use something else, right? How do you know what to choose? There's a lot of diagrams like this, trust me, in Coulson or Perry. Spend the time to look at them. And then in your report, if you convey or in your presentation that this is why I chose a reciprocating and not an axial, then people like it. People like that you put a lot more thought to it. Pumps, centrifugal pumps. Everyone selects them. How do you know which pump and what efficiency and things like that? So go to a vendor. This is KSB. A lot of people who sell centrifugal pumps, based on the flow rates and the head. Y-axis is the head, x-axis is the flow rate. These are the curves for various pumps. And this is how you select whether you want pump 32 or pump whatever, 200. Right? Because for whatever application you're doing, if you've done the sizing correctly, you know your flow rates and heads. Now you select a pump, and conversely, I show you, this is from a report. They say, okay, taking the mechanical efficiency is 80%, right? One way is to just assume, but a better way is to look up the curve of the pump, find your operating point, and then you can say whether it's what's the real efficiency, right? You don't have to do it for every pump. All I'm saying is you do it once so that you convey that you know how to do it, and you've gotten your hands dirty at it. We'll skip this. Have all your data ready. That's the have a very, I recommend at the very first meeting, you should have an Excel already with all the components that you have ever encountered for your project, with all their boiling points, molecular weights. It will just make your conceptual design much easier. Because if you have to look all of it, then things become very difficult. Instead, if you have a slide or a sheet where all the parameters are there, your VLE equations, right? The NIST website will have all the Antoine coefficients. But you'll have to put it in Excel and plot them, so that then your relative volatilities or other things are readily available. If you have a liquid-liquid system, Perry has a lot of these diagrams. If you're lucky, you will find it. Otherwise, search and see whether somebody has looked at your system, because you will need the VLE data or the LLE data if you're doing a liquid-liquid extraction. If you have a solute, will it precipitate? Always think in number of phases. If you have a reaction, is it single phase, 2 phases, 3 phases? If you have a hydrogenation, you may have 2 liquid phases, hydrogen as a gas and a solid catalyst, right? All the design is based on phases. So always figure out, is something going to precipitate, or is it, what's the solubility product? And again, these are things which are available. Somebody is going to do a NaCl or things like that. You would have it. Yeah, let's skip this. We already covered. That's it. Okay, and we'll share the slides. We went rather fast, but hopefully it helps you. So let's see, a lot of it is pretty ambitious, we agree, but let's see who produces a 3D design. We don't know, but let's see.
Thank you. And thank you for patient listening. Really happy. And that's all we have. Is there anything to add? Guru, you have anything to add? Anybody else? Jyoti? Abhijit? Okay then. See you all later.